This is Spencer Snowling from Hatch, and I'm glad that you can join us today for this month's GPSX webinar. So today we're going to be talking about modeling inorganic precipitation in GPSX. This is, I think, an important aspect of doing activated sludge modeling, the inorganic part of it. I mean, it's a biological system, so we tend to focus a lot on the organic things that are happening. But the inorganic side is equally as important, and we spent a lot of time in the development of GPSX to be able to model that really well and have that be properly captured in the whole system. So as per usual, I have some slides that I'm going to share with you. We're going to explain how precipitation works, but before I can do that, I actually want to tie in sort of how the inorganics part is built, and then how we do pH modeling and so on, because that'll be relevant in the discussions a bit later in the webinar. So I'm going to do all of that. I would put this in maybe the category of one of our more detailed webinars, where we're going to get into the weeds as we speak along here about the equations that we're using to do a lot of the speciation of these charged components and so on. So if you have any questions, please take the time to go over to the chat and put them in there, and I will hang around at the end of the webinar and answer as many of those as I can. All right, so let's get started. So basically, my plan is to sort of start with an explanation of how we got from the original ASM models, which don't have anything at all in them with respect to inorganics, to the stuff that we introduced into GPSX over the years. I'm going to give you a little tour of the history of GPSX as we made changes and improved that aspect of the software, and then I'll get into sort of how we do pH and alkalinity, and then the precipitation as well. And then I thought I would end up with maybe a little quick rundown of all of the unit process models that you can put on your drawing board that have a specific direct relationship with some inorganic aspect of it. So, your Struvite recovery and that kind of thing. And as always, I have a number of small demonstrations that I'll run for you live, and then we'll stay around and answer some questions at the end. Okay, so as I'm sure the inorganic aspect of activated sludge is really important. And by inorganics, I'm talking about the presence of those cations and anions that are there in the system, and any other things that, like volatile fatty acids and things that are going to cause a change in that pH. So it's not entirely completely just organics. I'm going to talk a little bit about acids and other things too. But basically, I wanted to cover, all the stuff that's not growth and death and nitrification and all of that stuff. So all of this is really important, specifically around the concept of the precipitation of, inert solids and inorganic solids in that system. This idea that we deliberately want to, in some cases, precipitate out things like soluble phosphorus. That's a key aspect of doing treatment, chemical phosphorus removal. But at the same time, they can also be a significant nuisance at treatment facilities. And I'm sure you know that I'm talking about struvite. That's basically one of the most common things that we do have problems with. And I'm sure you've probably seen pictures like this before, where struvite is a mineral that precipitates out magnesium ammonia phosphate that can form on the inside of pipes or on the walls of your digester, or even your primary clarifier if you're bringing back really high concentrations. These things can really be very expensive and very difficult to deal with. And so it's important for us to be able to make GPSX do a good job of predicting the circumstances under which this thing could potentially happen. So on the other side, on the sort of the positive side of all of this, is there are a number of technologies in the wastewater market out there that focus on deliberately causing struvite precipitation to happen, and that is to recover the phosphorus and then produce it as a product that can be sold, so for like fertilizer and so on. So I won't go into a lot of detail about these things today. We may come back and have that as an entirely separate webinar, but I just mentioned that there are a number of companies out there doing that. Okay, so let's start with the very, very beginning, way back in the 1980s, and talk about how we went from the beginning to where we are now. By the way, I will mention, I did realize just earlier this week, as I was starting to prepare this webinar, that we recently had the 40th anniversary of the founding of Hydromantis, the company that has originally developed GPSX. We were, of course, now part of Hatch, but I joined in 1999, but the company was actually founded in 1985. So I'll give you a little tour. I'm going to show you some older versions of GPSX as we went along here as well. So the original ASM1 model, that is sort of the first industry-wide accepted version of an activated sludge model, did not include any state variables for inorganic components at all. So if you look at the matrix, this is a scan right out of that report, and I realize it's super small font, so you're not going to be able to read it, but there is only one column that is not COD or nitrogen, and that is this alkalinity column. And so in a way, it's actually a very clever modeling of alkalinity. There's some stoichiometric relationships when you have growth and death and nitrification and denitrification that's using up or producing alkalinity. So you can measure it. You'd specify what your alkalinity was in the influent, and then a certain amount would be used up or generated as it went along. So it's not doing a charge balance or anything like that. It's basically just adding to and subtracting from whatever was coming in the influent. So basically, in those earlier versions of GPSX that were from back in the day, version 3 and older, which looked like this, we didn't have any inorganic components to be able to calculate the TSS from. So we could get VSS from the particulate COD, but how much other stuff was in there and adding into the TSS was kind of an arbitrary choice. So our simulator and across the industry, there was an assumed VSS to TSS ratio at various points in the treatment process. So that's what we used to do. Now we have improved upon that. First of all, when we went on and the industry moved on and we went to ASM2, that was the introduction of some inorganic components for the very first time. XMeOH and XMEP were metal hydroxides and metal phosphates that were part of the biological matrix, and so they could be tracked individually from everything else. And actually, TSS is a state variable in the ASM2 and 2D models. Now, we didn't implement it that way ourselves, but that is definitely what's in this particular report. So when you have those state variables there, we then had rates for the consumption and generation of these particulates and the TSS and so on, right there in the matrix. But what we did was, and starting in version 4, was we added our own new variable called XII, Inorganic Inert Particulate, and that exists straight to this day. It's an important part of your influent characterization, and it's supposed to represent kind of like anything else that is a sort of non-COD component. It's a particulate inert inorganic component that kind of is the catch-all of all of the other stuff that isn't already accounted for elsewise. So you've got all of those materials. It is a mass balanced and integrated, and you have to specify it as part of the calculations you're doing in your influent characterization, and it makes up a significant part of the TSS. Now that's useful to us because now we can actually track it dynamically. We don't have to have any assumptions. We can say, we know it's this much of our influent flow, and it can be mass balanced along with everything else. And this is the approach that we have now been using for 20 years or more. So this is what version 4 looked like, and so as we were moving forward in time. Okay, so now we have those inorganic components set up in that older version, and we now have that XII variable that we can work with, and there's some other precipitates as well. So this is how we get to our total solids number. So as you know, there's all these different types of COD that we have in the model, and we're calculating and predicting the concentrations of all the different biomass types, all of the different decay products, and slowly biodegradable substrate, particulate inert COD, and so on. And all of that can be added up to get your particulate COD number, which you can plot from all the different connection points in your plant. So we want from there, we divide by the VSS to TSS, sorry, the COD to VSS ratio, and that gives us the VSS number. And then we want to calculate TSS from there, but we need to know this other inert part. This is the part that was previously missing. So, in essence, what GPSX now has in its modern form is an inert biomass component. Each type of the biomass has a little bit of an inert particulate material. Of course, all the precipitates that I'm going to be talking about later on, like Struvite, and then that XII number, the other sort of catch-all other inert inorganics there. And all of those can be added up to get your ISS, and then we add those two things together to get to TSS. Now, I've gone through all of this tedious detail here because I kind of wanted to give a context for how we got from where we are to where we are today and the level of sort of complexity about what's going on in the background. I know for the most part, it's, everybody wants to plot TSS throughout the plant and understand how it works. And I just want to make sure that everybody understands there's this kind of complexity and sophistication going on in the background. So for the rest of today's webinar, I'm just going to talk about this part, just the inert inorganics part. Okay, so starting with version 6, that was when we developed the Mantis 2 model. That was released in 2010. We now went with a complete redo of the entire inorganic part of the model. So we now had several state variables for the soluble inorganic parts, calcium and magnesium and so on, and also the particulate things that could potentially fall out of that system as well. So we have calcium carbonate and other things in there too. So those state variables have now been added to the matrix. We then have rates in the model matrix for those. We have a full pH model, a charge balance model. So we had to go through and figure out which of all of the state variables are ones that dissociate. And we have to calculate their charged components from that. And that requires us, and that's how we built our pH model, which I'll go through here in a shortly. All of those pH calculations are handled with its own separate solver. And then at that point, we're able to start introducing in new models and new unit processes that were really about that chemical type of treatment and did focus a bit more specifically on inorganics. So this is version 6 of GPSX, that sort of dark gray background color that we were using at that time. Okay, so now let's talk about the state variables that we now have to work with. So now I was giving you the past, now we're up to the present. So here we are. This is screenshots that I did this week. Soluble inorganic state variables. We have it's total soluble inorganic carbon. This is your sort of dissolved carbon dioxide. And then we have these various anions and cations that are here. These are part of the soluble ones that we have that are just going to float through the plant, and it'll interact with things and be part of the calculation of pH. And then we have these particulate ones. These are solids that will settle out in the clarifiers and so on. There's our inorganic inert particulate that I was mentioning earlier. And then all of these precipitates here. So there's these aluminum, iron, calcium, and magnesium precipitates here. The one that everybody's most interested in, Struvite, is down here at the bottom. And then we now have rates to generate and figure out when these types of things form a solid and then fall out of the system and can be settled out and removed. Okay, now anything to do with precipitation is going to have us required to know what the pH is going to be. So I'm going to spend a few slides here talking a little bit about how our pH model works, and then we'll get into the precipitation part after that. Okay, so there's lots of stuff going on in these bioreactor calculations. There's lots of things happening simultaneously as part of our mass balance. So we have all those concentrations of the inorganic components that are coming in. We have reactions that are consuming or releasing those things with biomass growth and death. So when you're growing some biomass, you're sucking up some calcium and various other things that are happening. We also have the precipitation and dissolution process. That means we're forming solids or potentially dissolving them again, depending on the solubility product and so on. We have all of those speciation calculations to take things like the acids and ammonia and whatever to sort of figure out how much of those concentrations are the charged form. So we have those, and then once we have that, we can then do a charge balance to be able to figure out what the pH is. And all of that's happening together all the time, and it's dynamically being calculated as your simulation moves along. So many of these processes are dependent on each other, and that's actually where the real challenge is with being able to solve a lot of these models. And also on other factors like temperature and various other things that are going on in the model. So we need to be able to understand exactly what's happening, what are all the effects, what is the mass balance, how much is coming in, how much is going out, and a lot of those things are dependent on the pH itself. Okay, so now let's spend a little time talking about how we actually calculate the pH. So we have essentially these 6 weak acids in our Mantis 2 model, and they are can dissociate and can become part of the charge balance. And so we want to solve for what is the pH. We want to solve for what is that H plus concentration that you get when you start to do some dissociation. So those are all of those dissociation equations have dissociation constants in those. Those are temperature dependent. And the pH is then estimated by doing a charge balance. So one thing I should say before I leave this slide is this is the 6 that are part of the Mantis 2 model. If you go to one of the other libraries in GPSX, such as Mantis 3 or the process water library or the Mantis IW, there is more other components that are there. So if you go into one of the other libraries that has sulfur in it, those, sulfate will be part of this as well. I'll touch back on the process water library a little bit towards the end of today's talk. Okay, so look at this dissociation equation. Basically, what we want to do is understand for the total amount of ammonia as it's seen by the biological part of the model, it's actually going to be broken into NH3 and NH4 plus, and the relative distribution of those is a function of pH. So where does it fall on that pH scale? You're going to have more charged or a bit less charged depending on where it is. And that's a very simple, straightforward equilibrium calculation that you can do. This is our equilibrium relationship. I'll note here, by the way, these square brackets, we're dealing in moles when we look at these kinds of equations. And this is the equilibrium constant here, or dissociation constant, as we sometimes call it. And so that can be rearranged so that we can write the charged amount of the ammonia here, the dissociated part, is a function of the pH itself. So we're gonna write all of those different types of dissociated concentrations as a function of H plus, and then we're going to solve for that. That's basically how this works. We're basically doing electroneutrality, a fundamental concept of geochemistry. Basically, you can say that in any sort of reactor that you have, and you got all these concentrations of all these different charged species, all of those ionic species, the sum of all of those charges must add up to 0. Otherwise, you'd kind of have a current going around in there. So basically, we know that if it's going to be 0, we can rewrite all of those equations as I was just doing there. And then we can total up all of the positive ones and all of the negative ones, and then solve for the pH, solve for that H plus value. Okay, so I'm going to write this out in kind of an equation format here, just to kind of, if you prefer that way of talking about it. So let's start with the concept there, electroneutrality. The sum of all of the positive charges, the cations, need to be the same as the sum of all of the negative charges. And so the reactions and the dissociation would move around to maintain that electroneutrality as concentrations change and things go on. So as far as we're concerned in the activated sludge world, these are the main cations that we mostly worry about. In addition to H plus, the thing that we're trying to solve for, we have these other ions that are in solution: sodium, potassium, calcium, magnesium. Those are known by mass balance in the model. And then this other one over here is our charged one that is going to be a dissociating thing that we have to solve for. And then we have the same thing on the anion side here. You can see we've got OH and chloride, and then we've got nitrite. I included nitrate in here just for the sake of completeness. It never would occur in a charged form in the pHs that we see in an activated sludge plant. But anyway, it's here for now. Then we have sulfur, if that's relevant to your particular layout that you're using, and then the carbonate system and the phosphate system here, and also the dissociation of water. So basically what we're going to do is we're going to rearrange all of these so that they're a function of H plus, plug them all in, replace this OH here with this equation, and then now everything is either known or a function of H plus, and then we can solve all of this simultaneously for H plus. Now, that's sounds easy when I explain it, but it's actually a fairly complex mathematical thing to juggle, and we've spent a lot of time over the years getting our charge balance to solve quickly and accurately and do a good job. And we fine-tuned that now. We got it down pretty well. Okay, so once we have the pH, we can then also calculate the alkalinity, which is a number that most wastewater engineers want to know about. So once that pH is known, we can then plug it back into all of those equations to get all of the relative acid neutralizing components and be able to calculate what that alkalinity is. So we actually calculate several different kinds of alkalinity, actually. So you'll see carbonate alkalinity is the one that most people like to deal with, and the sort of intuitive one that people mostly understand. So that's going to be just the HCO3 and CO3 2- concentrations that are there, and also the difference between H and OH. That's summed up and then converted with a molecular weight calculation here to get to this kind of a number, like 150 or 100 or 200 or something like that. That's the number that I think most of us are familiar with working in, milligrams as calcium carbonate per liter. It doesn't necessarily need to exist as calcium carbonate. That's just a convenient way to represent it. That's carbonate alkalinity. Total alkalinity is basically all of it. So, and if you go over to our process water library, we even have other definitions of alkalinity over there too. Right. Okay. So the key thing is you want to be able to get this number and plot it and take a look at what's going on. So all of the pH and alkalinity calculations are available from this same menu. So if you right click on any connection point in your layout and go to the output variables menu and then go to the pH and alkalinity and ORP menu, you can find those numbers there that I was just talking about. If you actually hit this more button, you can interestingly actually get at quite a lot more. You can look at, after we've plugged the pH back in again, the individual charged concentrations of each of these things, which actually can be really quite helpful if you're doing something like trying to inhibit NOB growth, through free acetate inhibition or something like that. I want to look at what is the acetate charged version of that, or what is that concentration, not total acetate, but just the free version of it. That is really interesting because I can plot all of that stuff from that menu. I will also just briefly mention here that our new ORP calculation is also on this menu. And if you haven't had a chance to, didn't have a chance to join us last month, I talked about it and did some demonstrations about how our new ORP model works. So you can go to our YouTube channel, youtube.com/hydromantis, and all of our webinars are recorded there. And if you read at the very top was last month's, and that's where I was talking about what's new in GPSX, and I was talking about ORP there. Okay, so let's get on to do a little bit of demonstration here. So I want to just start with a very simple titration. This is actually something that's available in our sample layouts menu. And you can open this up here, file sample layouts. There's quite a lot of demonstration stuff, and I usually like to use those in our webinars. So basically, this is not a bioreactor as much as it's just a regular reactive vessel. And so we're going to start out with a completely clean water and just a little bit of cations. And then here's hydrochloric acid that we're going to add to that particular system. So if I just run over here and then just run a quick demonstration, we can see as I was slowly adding the acid, it is basically doing a titration. And as you would expect, you see that kind of break point right here at the point at which the anions and cations pass over each other. That's where you would see this drop in the pH here. So we, when we were originally developing the pH model, we did a lot of experiments in the model like this just to make sure that everything worked exactly as we would expect. And so, so that's there and ready to go if you ever want to do a titration type simulation. Okay, so let's move over to a more wastewatery one. So I want to do this one. So this is basically a conventional activated sludge plant here. We can see we have an Influent primary clarifier, regular plug flow bioreactor, secondary clarifier. And this bioreactor has all of the air just controlled by DO control. So it's basically 2 milligrams per liter across all of the reactors in the system here. So I'm just going to run a steady state solution. We also have the ability to dose some caustic here if we want to as part of our pH control, but I just wanted to give you sort of a feeling for what's going on with our pH model. So right now, if I look here, so just for those who might be new to GPSX, I'm looking at the concentrations as we go from left to right here as it goes downstream through this plug flow tank. We can see the ammonia is coming in, it's 35. I kind of loaded this one up a little bit, so we're doing lots of nitrification. And it drops to 2.6, and by the time we get to the end here, it's less than 0.1. We're doing like completely full nitrification. We've got lots of SRT and oxygen here. So it's going fully over to nitrate, and if I slide down this table, we can take a look here at the alkalinity number. So alkalinity coming into this tank is at 255, and it goes all the way down to 16 by the end. And that's really an indication that we're using up like most of the alkalinity. There's a lot going on. In fact, we are indeed running out of alkalinity here in this particular case. As you know, when you're doing nitrification, you're releasing some H plus into that system, and that's an acid. So it's decreasing the pH, and we can see that right here. So when we don't have the alkalinity there to kind of protect against that pH drop, to sort of suck up those H plus ions, we now see here that this is now starting to drop from 6 down to 6.1, and by the time we get to the end, it's 5.8. So that's kind of a measure of how you could look at the way this works in this particular system. And now we can play around with the model and see what else is going to happen. Like say I was actually in a spot where I had a lot more alkalinity in my influent water than I would otherwise. So I increased that from 250 to 350. And so instead of dropping all the way down to 5.8, it now actually hangs up here at 6.7. So and then that's all good. It's now going to run fine, and we won't have any particular impacts. So again, your influent characterization should have some thought towards your pH and your alkalinity, because it can really play a role in what's going on downstream in your plant too. So I'm just going to reset that. And also, I just thought I'd mention here, this is typically a way, if you wanted to do a little pH control, you could do that by dosing in here. So let me throw a little bit of NaOH in there, and we'll run that again. And so that's another different way. We can see if we can keep our pH up from that 5.8. So that's up a little bit if we weren't really overboard. So let's put 1,000 in. Then we would be well above what we needed. And now actually pH is going up because we've added it, and we've brought the pH all the way up to 7.5 before the nitrification got going. All right, so just to give you a feel, this is the row, and I find it the kind of the easiest way to sort of see what's going on in a plug flow system. If you were doing, 5-stage Bardenfo or something where you got nitrification and denitrification going on, and you wanted to plot this kind of a graph and table, that's kind of a nice way to see what's happening with your pH, your alkalinity, and your DO and other things that are going on in that system. Okay, so that's what that looks like. I'm going to go back to the slides. And let's talk a little bit now about the precipitation. So now I've kind of laid the groundwork there of how we have all those inorganic components. I've showed you how the pH and alkalinity is calculated. So let's get on to the actual precipitation part of this. So as I mentioned, we want to be able to calculate the amount and the occurrence of things like the precipitation of struvite. So we have to keep track, and we do mass balances on all of those state variables. And then we also need those rates. We need them in the matrix itself, the ones that generate these things out of their fundamental components. And so in our model, the Mantis 2 model, and the other models that we have as well, we use this general approach here. This is kind of a simplification of what we're actually doing, but it generally works like this. The rate at which we are generating something like struvite is this rate constant times this thing here, which is basically the molar concentrations of the components multiplied together, minus the solubility product. Now, we also have this thing here on the end, this switching function for the dissolution of that as well. Like if you were dissolving it back into the system, it doesn't happen at exactly the same speed as the formation. So, but for the most part, the important part is the bit in the middle here. So essentially what we're saying is we need all three of these components to be present, and we have this solubility product. So this is how we control the formation. Now, if we had very little struvite existing, and this was close to zero on this side, and we had lots of these components, then this would be a positive value, meaning that it is going to produce struvite. And when we run out of some of those components, or there's some of those components are missing, then this number will be close to zero, and we might have a lot of struvite around, in which case it's going to be a negative number, and it's going to release all those components back into the system. So it's kind of an equilibrium approach, but done dynamically through this particular rate. This thing over here is the thing that controls how fast that happens. They are, in general, quite large rate constants because the chemical precipitation happens quickly, like compared to the growth of AOBs or something like that. These are all really fast reactions. And this is really a nice, elegant way to do this. If even just one of these three things is missing, then this whole thing, when you multiply it together, is going to be pretty close to zero. And then, we're not going to be forming it. So that's how we sort of control. We need the presence of everything. We need the right pH, and then stuff can happen and form struvite. Okay, so let's do a demonstration with that. So let me bring back my GPSX, and I want to go over to, which one am I doing now? This inorganic. Yep, there we go. Okay, so let's quickly take, hang on, let me close these slides and make this bigger. There we go. So I'm just going to run this at steady state. And so what we're going to see here, once this goes down, this is basically a conventional activated sludge, and we're taking the wasted solids over here, going through thickening and into this digester. And I just wanted to show you the precipitation of the struvite that is happening there. So I set this up such that it had, the right types of components to be happening. So first of all, let's take a look at what's going on in the activated sludge tank. We can see here that we are removing a lot of ammonia all the way down here. That's fully nitrifying. We're not really doing much with the phosphorus. And then all of that's going over here to this anaerobic digester. So the digester's got 26 days, so that's lots of time, and it's doing your usual gas production and VSS destruction as needed. And you can see in here, if I just quickly look in this table, as the ammonia comes in, it's very low, but it's actually 16, almost 1700 going out. That means we are, of course, releasing a lot of nitrogen back into the system as ammonia as all of those biomass what VSS was destroyed, and releasing that nitrogen back into the system. Basically, same thing with phosphorus here. So these are pretty big numbers compared to what was coming in. In fact, I put it all on nicely together on a table here. Here's our incoming struvite components. And we can see that they're actually relatively small, but once all those solids get destroyed, inside the digester, these are the components here. So those are high, and look at what happens to our magnesium. It's 50 going in and only 0.15 coming out. That means that it sucked up all that magnesium to form struvite. So here's our struvite concentration, and we can see indeed that we have formed quite a bit. So this will allow you to sort of test out and try to sort of see what the conditions are going to be, how much struvite might be produced under different loading conditions and different operational settings, and different influence. I will show you here, for example, we know that since this is very low magnesium on the way out, it must be the thing that is sort of like the rate limiting step here. And in fact, if I go to the Influent and I reduce this magnesium down and then rerun this simulation, we can then see here that previously this number was 1200 or thereabouts. And then now this is dropped down to 927. So we can see that basically that was the rate limiting step, and we can see how we're generating that, and it can become part of your overall solids balance of your plant, and you can take a look at what's going on. I will mention, by the way, the digesters are treated as a completely mixed tank. So this little pump connection point down in the corner, you might feel that that's sort of like where the struvite could be removed from. Just keep in mind that it's actually treating this as one completely mixed. So the effluent number and the pump number are going to be the same thing. If you wanted to sort of show, yeah, we're somehow removing the struvite off of the bottom of this digester or something, you could put a solid separation unit after this and then just capture all that struvite. Okay, so now let's go back for one last bit of discussion here. So now that we kind of understand how all of these bits and pieces fit together, I did want to touch on a few unit processes that are relevant specifically to inorganics. So first of all, as I've mentioned previously, there are many different individual unit processes where inorganic components are being converted. And by converted, I mean potentially forming or being, dissolved. Any place that you see sort of these brown units, any one of these biological units, including the biofilm ones and everything, those precipitation equations are happening in those particular units, so you can potentially see some of those things happening. And of course, that does include the digesters, the anaerobic and aerobic digesters. And this is, of course, you don't have to do anything special to make the struvite happen. If the conditions are correct and you've got the right concentrations, those things will just come to light, and that particular rate of the matrix will be activated. Okay, so that's from the biological side. For as far as inorganics are concerned with solid separation, there are some situations under which your inorganic solids might be a little bit preferential on the solid separation side. So in our clarifier models, there's some menus. If you go to the bottom of the settling parameters menu, you'll be able to see a long list of state variables there and a multiplication factor. And so we've had a few times, especially in the primary clarifiers, where you might have for your particular setup in your influent characterization, you might want to say, as it goes across that primary clarifier, there's like some silt or whatever in there that I'm counting as a particulate inorganic component, and it settles out in the clarifier a little bit better than, say, the flux or whatever you've got in there. And so you could apply a little bit of a preferential settling term there to those inorganic components, and then that will help balance your VSS to TSS ratio on the way out of your clarifier. Now, all of these units over here on the right-hand side are solid separation units that are usually part of your biosolids handling system. They all have what we call the differential model, meaning that you can set the capture rate. These are empirical models as opposed to the 1D settling models or the biological models. These are basically just specify some sort of capture rate, and you can do that on a component by component basis, which does allow you to do the inorganics a little differently than the organic. So I took this from the hydrocyclone, where you can see here that the removal efficiency of the particulate inert material is a little bit better than it would be for some of the biodegradable ones. Okay, now that's with respect to solid separation. If we go ahead and look at some of the soluble inorganic components here, just quickly mention these two objects. These are in the Influent panel at the very top of the list of objects you can put on the drawing board. And these are for acid dosage and alkali dosage. They were parts of some of those demonstrations that I was doing earlier. And you can go ahead and put these down and go to the feed chemicals menu, and you can see all the different types of chemicals that can be dosed. Typically, these two things are, of course, used for pH control. And so those are all there, and they're following and using, or they're adding the components that our pH model will react to, I guess is what I'm getting at. We also have a whole separate other object here called the inline chemical dosage object. This is primarily there for doing phosphorus removal. So this allows you to add alum or ferric chloride or any other number of types of chemicals. And you can add that with, to basically remove the phosphorus, and it does actually take out a few other COD things and a little bit less preferentially as well. So this is a standard feature that's been part of GPSX forever. As you may know, it has a very sort of non-stoichiometric relationship here. So if we look at this graph, this is right out of our tech graph, you can see the amount of metal that's required to remove something is a flat relationship until you get down to very low concentrations of, say, phosphorus. Then you have to add a lot more metal. So this relationship, it starts out stoichiometrically, but then we have this sort of switching function at the end, and it kind of drops off as well. So we have parameters to be able to calibrate that curve. It is also a function of pH. So you can see the pK, the solubility product here for alum, for example, is here. If you were, say, for example, running the model and you found that your dosage, you have the dose amount you're dosing correctly in there, but you're finding that you're getting a little bit worse or better performance, you want to dial it up or down, this is the parameter at the top of this menu that you would use to sort of calibrate the performance of the phosphorus removal in your system. And of course, that does then form a sort of metal phosphate, and then it goes into all of the other mass balances that I was showing you earlier. And as you know, of course, settles out in the clarifier, and you can remove it as a chemical solid. Now, I will mention, by the way, if I go back to the earlier menu here, in this menu here, there were previously some other options that were here. We've now added a volume-based option. We used to have basically dosing by mass or dosing by concentration, but we now have dosing by volume as well. That's a new feature that's available in version 9 of GPSX. All of this kind of stuff is actually a really interesting aspect of what we can do. And I really wanted to point out this previous webinar that we did last fall, optimizing chemical dosage with GPSX, where not only are we exploring behavior of the model, but we were using some of the advanced GPSX simulation tools in there, sensitivity analysis, and using the optimizer and Python and other things. I think this is one of our very best webinars, actually, and so I just encourage you to take a look at that one if you have an opportunity on our YouTube channel. Okay, and then lastly here, I will mention that there are some units, as we talked about earlier, that are designed to specifically force the precipitation of struvite with the idea that it will be able to recover. And so we have a couple different struvite recovery units. And so I will mention we did an entire webinar on that a couple of years ago, and it's also one of our really good ones. And so I do recommend jumping in and taking a look at this modeling side stream nutrient removal webinar that we did some time ago. Okay, one last demonstration here. Back and grab the struvite example, this one. Slides. And I'm gonna just run some steady state here. One thing I should mention is, I guess I can do this while this is running. If I go to the kinetic menu here, in any of the objects, this is where you can find a lot of those parameters that I mentioned earlier. So the kinetic menu is where all of the kinetic rate constants are found. So on the biological side, which is the top part of this menu, this is where you'd find growth rates and decay rates and half saturation coefficients. And we have 10 different biomass types. So that's a fairly long menu. You got to slide way down here until you get past everything. There's hydrolysis, and then we get into the chemical stuff. So here you can see, for example, this is the struvite king. There's our precipitation and dissolution rate. That's that rate constant I mentioned earlier on that slide. This is the solubility product, and that's the switching coefficient. So you can see these numbers here. To be honest, I don't find that I have to ever change these very often, but let's say you're in a situation where you might want to, you consistently are a little bit over, under, you want to adjust it. These are the parameters that you could do to control that and to dial it into the data that you have measured. Okay, so basically, I just want to mention this unit here is the Struvite precipitation unit. This is the anaerobic version. And so it's basically a granular anaerobic reactor. It has a solid separation unit built into it that is basically driven by the formation of granules. And so the more solids that are in there, the capture rate is driven by that sort of a special model that's in there. We have in fact done webinars on this particular object as well, if you want to go back and take a look at those. But very quickly, I'll just point out that in this particular layout here, the solids that are being taken are thickened, sent to the digester, and then the returns are brought up through this dewatering, and then these very large concentrations are being sent to the Struvite precipitation unit. There is magnesium and pH control up here. They're basically there to sort of give the optimal setting for optimal concentrations to form Struvite. So if I take a look here on what's coming in, the influent column here, we can see the ammonia coming in is 1281, drops down to 188. And the soluble phosphorus drops down to 169. So we are certainly forming a lot of something. So we can see here it is Struvite. This is a huge number here at the end, and it's doing that in that reactor. So as I mentioned, we could, I won't go into a lot of the details of that today. We have some other webinars where we've covered that in more detail. Okay, back to the slides. Now, there's a few other things I wanted to mention before we wind things up today. I always really try to emphasize, and if you've been to our other webinars, you know we talk a fair bit about influent characterization. It's also something we talk quite a lot about in our training sessions. Usually I'm normally talking about characterizing the COD that comes in, you know, how much of it is readily biodegradable, etc. But it is also equally important to actually get your pH and alkalinity right in your influent as well. So when you go to set up your influent, go to the composition menu, select influent characterization to open up Influent Advisor, the tool that you enter in and see all those calculations. In the left-hand column, at the top is where you normally enter in those numbers that you have and some of these fractions which you might have to adjust as part of your calibration. But farther down the list is the pH and the alkalinity here. So you're asked to enter those. And if you're put those numbers in here, they get used. And then I want to just zoom in here so you can see it better. Point out that below that are these inorganic compounds. Now, these are the ones that could potentially be really important when it comes to, you know, the formation of precipitates later on in your downstream in your system, potentially in your digester. So I, in fact, showed in that earlier example how the soluble magnesium was really important to how much was being formed in that digester. So it's really an issue of what's in your influent too. Now, I have in the past not really had very many projects where we had a lot of detailed sampling and data around how much magnesium was in the influent, but certainly if the digester struvate formation was like the point of the modeling, then that is a number that should be out there and should be measured. Now, I will mention that if you have the pH model turned on and you're setting these numbers, it is going to adjust these numbers here in your anion and cation balance in order to make your carbonate and pH work a little bit as we go. All right, so I just mentioned actually, I will mention that you can turn off the pH solver if you like. There's reasons why you might want to do that. Like a lot of the time, just assuming that the pH is going to be, you know, between 6.5 and 7 throughout the plant, that's quite a fine assumption to make. And pH was not really part of the point of doing the modeling. In those cases, you could come here and turn it off. The advantage of turning it off is that the pH calculations are actually a fairly significant number of equations to solve. So if you're not solving them, then your model might converge faster and run faster. So it's basically just an issue of, as we often do, emphasize keeping your model as simple as possible. If I don't really need to know a lot of details about the pH, you can come in here, you can hit this Site Properties button, go to the biological model setting, and say set pH rather than estimate pH. Estimate means it's going to calculate it for you. Setting it means you're just going to say that it's 7 throughout the system or whatever number you want to use. If you set it, it'll run faster. You can actually even turn off individual precipitation reactions within our matrix as well. It's in that same menu. Just scroll down farther and you can see here at the top, actually, you can turn on and off individual biomass types. And here you can turn on and off individual precipitation reactions. Again, that might be partly because I just want to make the model. I don't need all that complexity. I can turn off parts of the model just to make it solve faster. And so sometimes we do that. Okay, one thing that I will mention that I talked about last month at the webinar that I thought I might just repeat this slide over again is that we do have a little bit different way of, or a little bit different default value here for the amount of CO2 that's driven off by diffused aeration. So previously this was a higher number and we've dropped it down. Part of that was for the reasons of pH. I think our experience over the years had shown us that previously we were kind of driving off a little bit too much CO2, and where we would expect to be able to see the pH dropping in the way that I showed you earlier, that wasn't happening. At least it wasn't happening all the time in the way that we would expect. And so over the years, we had kind of gotten in the habit of reducing this value here. And so now it is at a much better calibrated value. And if you would like a much longer and interesting discussion about that, you can actually watch last month's webinar and on our YouTube channel. And I go into a little bit more detail there. So lastly, I want to mention about our GPSX process water library. So as you may know, GPSX has a number of individual libraries, and they each have their own set of models and unit processes and so on. So the general one that you get when you just start up GPSX and run it is called Mantis 2. That's our main regular one. Probably 90% of everybody uses that one. But we do have this other one called the Process Water Library. It is essentially a water version of GPSX, and it was developed back in the day to do both drinking water and process water treatment. And it has a much longer list of inorganics in it. So at one point, I was going to actually do a desktop demonstration in it today, but I realized by the time I got even halfway into the discussion, it would be way too long. So we're going to leave the discussion about the process water library and its very special version of everything, maybe to another webinar in the future. But I just thought I'd mention it, that it is, the same thing I've talked about earlier, the same approaches, electroneutrality, charge balance, and all that stuff, but it is just more of it. So you can see here we've got sulfur and we've got manganese and copper and some other things in there going on. So, and actually a much longer list of precipitates as well. It also has its own individual unit processes that are not in the regular version of GPSX. So we have some other chemical units, ion exchange, and other things. And basically, its focus is not so much on activated sludge, although you can do that there. It's about doing chemical water treatment. And so we do have a webinar that we did several years ago about that. My colleague Rajiv Goel did. And so I invite you to go over and take a look at that. And we will hopefully be redoing that one with some more updated stuff in the near future. Okay, so winding things up, just a few thoughts. The Mantis 2 library, it has a fairly sophisticated approach to doing the water chemistry. There's an awful lot going on in the background. Normally we, when we're building models and doing activated sludge, we spend so much time thinking about the growth and the biology and what our bugs are doing. Sometimes the really interesting chemistry kind of gets lost into the background. So the models are really good at assessing the effect of the biological activity on and various chemical reactions on that pH and alkalinity and how those kind of things are interrelated with each other. But it does require, if you're going to, really do some detailed modeling around this, it does require more information than you might normally want to collect. So you might want to do some sampling around pH, around some of those ionic concentrations here and there. And lastly, of course, we have many processes in GPSX that are designed specifically to handle inorganics as we go along.